Hello back. So now, after a quick excursion into differential item functioning, let's see how that actually relates to what we're doing with multi-group CFA. But before we get there, how could we link these differential item functioning parameters to our equivalence levels? Well, I think the easiest parallel, or the most obvious parallels, are if we look at item discrimination. So that is essentially the slope that has to do with metric equivalence. And if we look at item guessing, the intercept differences, then this has to do, or that can be translated into full score or scalar equivalence. How does it actually now work? We need to go through a number of steps. We need to identify the factor structure, then we need to identify the latent score in which test takers are being matched, then we compare the performance on each item against our criterion of what constitutes differential item functioning. Remember, we have to think about how big is big enough for us to worry about, and then we have to make the decision of what we should be doing with the item, and then remove it, and then potentially repeat these steps again. So this is the classic approach for item response theory models. In CFA though, we kind of do the same thing, we just do it a little bit differently. And let's go through these steps. How do we actually run a differential item functioning approach or test in multi-group CFA? What we first test is whether our items load onto the latent variables. So if we have two different groups, we set up our model and we test whether there's the same overall structure, which of course is configural invariance, or if we use the Fontaine approach, it's structural equivalence. And how do we know whether we meet a condition of configural invariance? We would first of all expect that there's the same pattern of loadings in all groups, and configural invariance is supported if there's a single model which basically fits the data well. So we need to look at our fit indices. We need to show that all the item loadings are substantial, and that's a little bit of a rubber band, but should be significant. And there should be no large modification indices. So basically the model should represent the data reasonably well, and there should be no other parameters that should be included in the model in order to make the model fit better. And a final one is the correlations between the latent factors should be less than 1. Because if they're 1 or very close to 1, it basically means that the latent factors are one and the same. So if our latent factors correlate at 0.9, we probably don't gain anything by measuring, like two separate factors, because they're so highly correlated that they give us the same information. So recapping, how can we test configural invariance? We need to have a model where all the items load on their designated factors. The loadings need to be substantial and they need to be significant. There should be no large modification indices, and the correlation between factors should be reasonably small, should not approach unity. And of course the model has to fit reasonably well, so we have to look at the overall fit indices. So these are the kind of issues that you need to look at with your model, ideally in each individual group separately. And this is what we typically look at when we run, as you've seen in the other video, when we run our first CFA model and we just specify the group and now the program will estimate different or will estimate all the parameters separately by group. What are issues? As you know, if we have configural invariance, it doesn't actually mean that people understand the items in the same way. The factor loadings may still be different across groups, and essentially with configural invariance we have the starting point for further tests that actually tell us whether our instrument is working or not. If you don't have configural invariance, so your items do not load or your model does not fit, there's no point in going further. Basically, your instrument is not working well. Then the next step is metric invariance. So what we're looking at right now are the factor loadings, so the links between the observed indicators and the latent variables, whether the factor loadings are the same in group A compared to group B. So as I just said, metric invariance requires that the factor loadings are the same or statistically non-distinguishably different, so equal. We need metric invariance if we want to compare covariance-based statistics. So if we want to compare correlations across cultures or across groups, if we want to compare regression coefficients, then we need to show metric invariance. At this level, we cannot directly compare means, but if we have metric invariance, we can compare correlations, regressions, etc., etc. So you can run your regression model and you can test whether the effect of one variable on another variable is similar or different across groups. We might have situations where we do not have full metric invariance, and in those situations we can look whether there are individual items that behave a little bit differently, and so people have talked about what is called partial metric invariance, and we will get there in due course, where we can free up some parameters and then test the model fit to see what happens if we free them up. Do we get a better fitting model overall? So ideally we want to have all items to function the same way across cultures or across groups, but there are options of actually getting away with a model where we open up some parameters to vary across groups. Finally, if we have had our metric invariance tested and it is okay, then we can test whether the intercepts are the same. So whether the baselines or the guessing parameters in IRT terminology are the same or different across groups. Oh, by the way, one thing that I probably should stress, why do we test it in this particular order? It's essentially a convention which makes mathematical sense, because we have to start with a configural model, and then the first question really would be whether the items actually are connected to the latent variable. That's why we first test the factor loadings, and once we are sure that the factor loadings actually work, then we test the intercepts. So there's some kind of logic to it, but it's also somewhat of a convention. So if you read some older articles from the 1990s, oh my god, when dinosaurs were still roaming planet Earth, you will see potentially some papers that did it in a slightly different order, but today it's typically configural, metric, and then scalar invariance. So what happens with scalar invariance? We look at the item intercepts, whether they're equal across groups. If they're equal, then it means that basically the items are measured on the same scale, so we have the same 0 point and full score equivalence. I haven't really talked about the philosophical origins of the invariance versus the equivalence literature. May get to that at some stage. So there's a different philosophical origin, and this is where one of the points where they kind of directly converge, but mathematically, for all our purposes, invariance and equivalence are pretty much interchangeably. The cool thing with scalar invariance, and that's why we are so keen to test it, is we can actually compare our constructs, our means, directly across groups. So hooray, that's where we want to end up. And spoiler alert, that's actually not what we often find, but we will get there. Again, we might be able to cheat a little bit, and so what happens if we don't find full scalar invariance, we can have a look, and if there are some individual items that could be freed up to show different intercepts across groups, we can test whether that actually makes a difference. And if we have like 1, 2, or 3 potentially, we could free them up and then have a good model fit, and hooray, we can directly compare our results across groups. But we will get to that at some stage soon. So how should we go about this? First of all, partial scalar invariance is sufficient for cross-cultural comparison. So if we have partial scalar invariance, so at least some of the items work in the same way, and some others we basically free the item intercepts up to vary across groups, then we can typically compare our results. I just quickly want to mention that because you might see it in the literature. There are all sorts of additional tests that can be run, and they can be meaningful for a specific context. I just want to quickly mention them. If you see some older articles in particular, they may actually swap out some of these tests that I talked about, like metric or full square equivalence, and run these other tests instead. Don't do that. But these additional tests that I will talk about just now really briefly can be meaningful for specific purposes. The first one is same error variance. So we check actually whether the influence of unmeasured variables that influence our observed indicators, so basically influences on our observed indicators that are not due to our latent variable, are the same across groups. Error variance invariance is often used when we are concerned about, for example, reliability issues. Another issue that we can test is whether the covariances between the latent factors are the same or not. So are the correlations between latent variables the same or not? So that's something that can be quite interesting from a theoretical perspective. So for example, anxiety and depression, if we have a good instrument, is anxiety and depression equally strongly correlated in different environments? If it is not, what is causing that differential correlation? And we can also look at what is called factor variance invariance, so whether the variability of the latent variables is the same or not. This obviously can only be tested if, or easily tested if we don't constrain the latent variables to be equal across groups. There is some cross-cultural literature that suggests that factor variances vary systematically around the world. There's even some theories around that, like tightness-looseness theory. So it's an interesting test that can be run for specific purposes. So when do we actually need each level of invariance? It really depends on the goal of what we want to do. Obviously, we should have configural invariance, because if we don't have an instrument that taps into the same kind of construct, then we are looking at apples and spark plugs or something like that. And configural invariance is always the baseline model for any further invariance test. So whatever else we're doing, this is our baseline model, and we've compared the next higher level of invariance to the previous one. So this is our baseline. Metric invariance, as I already mentioned, if we have metric invariance, we can compare correlations. We can compare correlations, regressions, even mean patterns. But we can't directly compare latent means or mean scores directly across groups. We can only do that if we have scalar invariance. So it really depends on what you want to do in your study. If you want to run regressions and you want to look at the relationship between variables, you might only need to test for metric invariance, and you don't need to worry about scalar invariance. On the other hand, if you want to directly compare, let's say, ability levels between groups or anxiety, depression levels, so mental health scores across groups, then you need to show scalar invariance. right? So it really depends on the goal of what you want to do and where you want to go with your research. So, and what happens if you cannot find the necessary invariance level that you're shooting for? There are lots of options, and here really Bob's your theoretical uncle. The first thing that you could do is you could only use the items that actually seem to be working across cultures. So you chop down your instrument. As you might remember, that can lead you into devil's kitchen, because we may have domain underrepresentation, because it could completely change the meaning of and content of what we are measuring. And the flip side of that is actually, if you start looking at what items do not fit well across groups, so what items create problems, that can provide some very, very fascinating insights into the cultural dynamics. So if you are interested in amic research, cross-cultural invariance tests can actually be very informative about cultural dynamics from an amic perspective. So the interpretation of deleted items can be very informative and theoretically meaningful. We can look for partial invariance, so release some of the constraints, so we can try and see which items do not fit as well, and what happens if we actually allow them to vary freely between groups. So it's still possible to go ahead with meaningful cross-cultural comparisons if you have partial invariance. How many items you can actually leave free to vary across groups, that's again one of those big questions where people argue over a beer or over a million of papers between each other. There's some older literature that I think is quite persuasive. There's some more modern literature that basically says you can get away with just 2 items that show partial invariance, which I find a little bit problematic. But hey, and another option is actually you could also drop cultural samples. So if you have, let's say, you sampled 100 different samples from around the world, and maybe 95 of them seem to be working, you can easily drop those 5. If you're a poor student and you only have 2 samples from 2 different groups, once you start dropping 1, you're left with, oh, hold on, if you have 2 and you drop 1, then you're left with, oh my god, can I still do something with that? You get the point. So the real issue is you can actually remove samples from your analysis if one sample performs very, very differently for the particular test, but then obviously that raises all sorts of questions potentially for your thesis, for your project, etc. And that is it for the time being. So you're free to go about your daily activities, roam around in your house, stay safe, play with your kids, do some really cool work, and then do your homework. And we will talk soon again with all the stuff we haven't talked about yet, about multi-group CFA, modification indices, partial invariance, etc., etc. The cool stuff is still about to come.